Magnitude.
Oh yeah.
Oh yeah.
क्या बदतमीजी है ये, आराम से रहो।
CR, please look into the matter.
श्री राम के खिलाफ कौन बोल रहा है, बताओ जरा, नाम बताओ।
जय श्री राम बोला साहब।
CR प्रथमेश यादव, where are you?
CR, please look
Sir,
into
I am
the
here
matter.
only.
CR Prathmesh, please look in the matter.
Okay, good afternoon, cadets. Am I audible?
Good afternoon, sir.
Good afternoon, sir.
Good afternoon, sir.
Yes. Okay, thank you very much. Once again, a very good afternoon to each one of you. We have met physically during your practicals when we started with our practicals on Wednesday, 23rd. So we had met physically, but unfortunately, I'm sharing the timetable over here. Can you see the timetable?
Yes, sir.
Okay. Okay. So basically, I'll be conducting this course, which is basic electrical engineering. It will be done by two faculty members. One is myself, Kailash Minjay, as we have personally met, and second one is Mali Madam, Sujata Mali Madam. So she will be sharing this course with me. Okay. Now we could not physically meet in the last week because as we can see that on Monday, this lecture, okay, we could not have this lecture because we were having our first semester end semester examination. Then on Tuesday, I was having, so this is the lecture that I was supposed to be engaging, but because you had the examination on Monday and Tuesday, so we could not have this lecture, and we could not have this lecture for this particular course. Okay. Now I just want to know that. Okay. Okay, just give me a minute. I just want to know whether any lecture has been conducted by Mali Madam or not. Okay, okay. So, guys, I just want to know that whether we had this lecture. Did Mali Madam conducted this lecture? I just want to know. On Friday, had this lecture been conducted? I just want to know.
No, sir, no.
Okay, okay, fair enough. Right.
Yes,
So-
sir. On Friday, the lecture was conducted, sir. Of Sujata, ma'am.
Sujata ma'am. So ma'am has conducted the
Yes,
lecture. Okay.
Yes,
Okay.
sir. Yes, sir.
Okay, first class. So it should not so happen that nobody has conducted the lecture, right? So by and large, you are aware that what course you will be doing. So two of us will be sharing this course, which is called as BEEE, Basic of Electrical Engineering, Basic Electrical Engineering. And as you are aware that there are two faculties, one is myself and second one is Sujata Mali ma'am, who has already engaged the lecture. Okay, that is number one. Number two, as far as the timetable is concerned, okay, so as far as timetable is concerned, we have got something like 3 lectures in a week. Okay, so we have got 3 lectures in a week. So this is a lecture number 1. This is lecture number 2. And the third one is lecture on Friday. Okay. Now this happens to be something called as a combined lecture. As you can see that. So this lecture can either be conducted by myself or can be conducted by Mali ma'am, and that will be told to you either beforehand who will be conducting the lecture, so that you can come prepared or you will be in the right mental frame to expect who will be conducting the lecture. Right. So today I am going to conduct this lecture. Maybe next week Monday this lecture will be engaged by Mali madam. So if this part is understood, okay, please type in the chat box what you see. Feedback. Type these 2 words into the chat box. So please, I think there is some delay, but yes, okay. I have not got used to this delay in the chat especially, right? So everybody please type into the chat box, okay, so that I'll get feedback that you have understood, okay. And basically I'll get accustomed to the delay. When I ask you to do something, okay, let us presume that you have done it instantaneously, but how much time it takes for it to, to be reflected on my screen. So there is some amount of delay and becomes quite annoying because when in offline mode, I tell you something and you understand and you know you are here. So it is instantaneous, right? So that feedback is instantaneous. If you have understood, we come to know that you have understood. If you have not understood, we also come to know that you have not understood. First class. So this is what the arrangement will be. One lecture will be engaged by myself, another lecture will be engaged by Mali madam, and there will be a common lecture as we have got today will be engaged by one of the faculty member, which will be told to you well beforehand. Okay. So that is as far as the syllabus, that is as far as the conduction of lecture is concerned. Okay. Now a little bit about the syllabus. Earlier, that means your seniors who are in second year, they had a course called as BEEE. What we used to call as BEEE. That additional E was nothing but electronics. So we had basic electrical and electronics engineering. So now this electronics part has been removed. This electronics part has been removed and it has been put up over here, which should be done by two other faculty members, Karlika sir and Agar sir. Okay. Now one more thing, your seniors, they had two electronics. One was called as AEC, that was analog electronics, okay, which they had in third semester. And the second electronics is called as DA and PLC, which is basically digital electronics, which your seniors in fact are doing right now in fourth semester. So this is where we stand, cadets. Okay. So your seniors had a course called as BEEE, which was slightly tough because there was large amount of electronics component. So a decision was taken, syllabus was revamped, and that electronics part was removed, and it was altogether put up into the separate subject called as basic electronics. Okay, now this basic electronics, as I told you, is a combination of the two electronics your seniors are having. That means the old syllabus. So therefore, long and short of it, the electronics has been removed from BEEE, but it has been put up into basic electronics, and that basic electronics is a combination. Okay, so this basic electronics is a combination. It is a combination of analog and digital electronics. Okay, so that is how the things are. Okay? So this is as far as the syllabus is concerned. Okay, because you may receive a feedback from a senior thing that BEEE was very, very tough. So I don't agree with that entirely because BEEE was tough because of the electronics part, but that electronics part has been removed from BEEE. Now it has been made as BEE, and that electronics part is put up somewhere else. Okay, so that is how the syllabus and other things are. Okay. So if anybody has a doubt, can unmute and ask. Otherwise, please type into the chat box what you see. Okay, so far I have received, yes, couple of responses from Daksh and Inderjeet. Okay, let me have more responses so that I know that where we stand and we have got hold of the situation. That is number 2. And number 3, there was a demand, there was a request from division saying that, sir, we need what can be said as a notebooks and other things. Okay, so as you can see that I have already doing that exercise, and So this is the data which I have collected from the faculty members. What are type of notebooks they want to distribute. Okay. So I have got a very rough data. So I'll collaborate with the admin office and as early as possible, you will be given the notebooks as well as the textbook. Okay. So and Sefishu and the division. I think division one they have done practical today morning. So sorry. So they have received the boiler. Sorry, they have received the drafter as well. Okay, so this exercise I will do as early as possible, and will be given the notebooks which you can use for taking down the notes. Right. I strongly recommend that you take your notes. Please don't rely on the screen that saying that everything is available on the computer while I should study. Okay. So let's not have that kind of attitude because it will get us in trouble. Okay. So this is as far as the syllabus and other things are concerned. Please allow me to continue. So my dear colleagues, this is the syllabus that we are going to learn this semester. This is IMU syllabus, as you can see that. And the course that we are doing is basic electrical engineering for 45 hours, which has got a credit of 3. Now, this syllabus has been broadly divided into two sections or 3 sections, but major there are 2 sections. So this is section number 1. This is second unit, and this is the third unit. Now, as far as the syllabus goes, I think Mali madam must have told you that this part will be done by Mali madam in totality. The second unit will be done by me, as well as the third unit will also be done by me. So these 2 units will be done by me, but from unit 2, some of the part, that is electromagnetic induction and magnetic circuit. Okay, so this part will be done by Mali madam. So this part will be done by Mali madam. And that is how the syllabus will be distributed. Okay. Right. So if you understood this, please type into the chat box. I am habituated of doing something like this. Okay. If you understood this, please type into the chat box what you see onto the screen. ND stands for no doubt. Yeah, thank you. Okay. So many times when okay, thank you, Indrajit. So I keep on doing this exercise. I like to take the feedback if you understood, if you are not understood, and other things like that. Right? So I keep on asking you to type into the chat box ND, ND1, ND2, ND3, ND4 like this. Okay, depending upon the things that we have done. Okay. So once again, thank you very much. And before we start with this generation of AC, so I will like to touch upon this particular part. Okay, state that when the direction of flow of current is continuously reversing, is called as an alternating current or AC. Right. So what I will do is that I have got a small video which is very useful. Right. So by virtue of that video, I will show you that how generator works and how AC is being generated. Okay. So please allow me to share that video. So what I will do is that So I'm going to show you this video.
In this module, you will learn about an AC generator. An AC generator is an electric generator.
Okay, I have purposefully stopped it. Just you can quickly unmute yourself and tell me that is the video properly seen and is the commentary also heard?
Yes, sir.
Yes, sir. We
Okay.
can listen the audio also.
Okay, thank you very much. I'll continue with the video.
Generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, the armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily 0. Hence, the induced EMF at this position is 0. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then at time t/2, the armature again becomes vertical and therefore the induced EMF is 0. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes 0 momentarily at time t seconds as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal. In this module you have learned an AC generator is an electric generator that converts mechanical energy into electrical energy in the form of alternating EMF or alternating current. An AC generator is based on the principle of electromagnetic induction. An AC generator consists of an armature, a shaft, a field magnet, slip rings and brushes. The graph between the time and EMF generated by an AC generator is sinusoidal.
Okay, can you hear me, cadets?
Yes, sir.
Okay. I have shared onto your chat box the link of this video. So if you have received the link, please type into the chat box what you see. Okay, I have received response only from Dux. So let me have the other responses. Okay, others also type into the chat box what you see so that I'll get the feedback and I can move on. Okay. So again, I will revisit the syllabus and
Excuse me, sir. Sir.
yeah, please go ahead.
Sir, your loudly, sir. Your voice is very low, sir. Can you please speak loudly?
Yes, sir. Your voice is very low.
Okay. Absolutely, sir. No problem. So, am I audible now?
Yes, sir.
Okay.
Sir, you are audible, but your voice is very low.
Your voice is.
Sir, your micro, sir, is it your microphone issue, sir?
1 minute. What I did was I changed some settings I changed some settings. Okay, am I audible now? Is the voice better?
Yes, sir. Yes, sir. Better.
Yeah, thank you very much. See, what happens is that when I'm using this particular Zoom for video sharing, I have to do some changes in the setting, and probably because of which there was a voice issue when I switched back to the normal teaching. Okay, long and short of it, have you followed the video? Have you understood what it was trying to convey?
Yes, sir.
Okay, so this part we have done, and there can be theory questions, okay, into the exam, and you will have to describe the process in which the AC is being generated. Okay, or you have to explain the process of the generator action. Right. So we have seen the parts of the generator, and we have also seen how the flaming right hanger is getting applied. And because of the as there is a change in the direction of the movement of the conductor, how the current direction is reversed every half cycle. And number one, and number two, you have to correlate that with the help of the graphical representation. Okay. And the resulting waveform is in a sinusoidal form. Number one, the waveform can be divided. I will just recapitulate what it was done over there. Okay. So the waveform got divided into 4 sections. So the waveform is divided into 4 sections. So this is section number 1. This is not accurate or to the scale. And this particular one, so this particular one was marked as T/4. So this particular was marked as T/4. This was marked as T/2. This was marked as 3T/4. And this was marked as T. Okay. Now, please can somebody unmute and tell me what is this T business? What does this T stands for?
Time period required.
Time period.
Okay, time period, absolutely right. Time period for what?
For evolution.
Okay, so T is nothing but time period required to complete
One revolution.
one revolution, or what we can call as a one cycle. Time required to complete one cycle. Okay. Then we have got also something called as F. What is this F stands for?
Frequency.
Frequency.
Okay, okay, wonderful. F stands for frequency. Okay, do we remember the unit of this frequency?
One by T.
Unit.
1 by 2. 1 by second.
Okay, there are 2 ways in which this has been. There are 2
Hertz.
units. Very good. One unit is hertz, and second classical unit. Very unlikely you come across is called as cycles per second. Okay. Cycles per second. Right? So these are the 2 units. Okay, I just want to ask you that right now I'm conducting a lecture from TMI. So am I audible, or there is a disturb? I mean, there is, you can hear some background.
There's a lot of different.
Sir, you are not audible.
Background sound is coming.
Background
you are not
noise is also
audible.
there. Okay, okay, just give me a minute. Okay, am I audible now? Is the background noise still there or it is slightly reduced?
Slightly reduced.
Okay, okay, okay. I will try and devise some other method. Right. What we saw is there is something called as frequency. Frequency is nothing but number of revolutions completed in 1 second. The unit is hertz, and another classical unit is cycles per second. Okay, very old standard. You can say British textbooks. They use this unit, cycles per second. Okay, and T is time required to complete 1 cycle, and the interrelationship between F and T is, if I am not mistaken, F is equal to 1 upon T or T is equal to 1 upon F. Okay, do we remember this? The expression between F and T. Do we remember this? Yes or no?
Yes, sir.
Wonderful.
Yes, sir.
Wonderful. Thank you. Now let me do some very quick exercises. Can you tell me how much is the frequency in India? Frequency of electric supply in India.
50 hertz.
Very good, 50 hertz. Okay, great. Can you tell me that verbally how much will be T in this case? Don't tell me it is 1 by 50 hertz. I also know that. So do that calculation 1 divided by 50 and tell me the answer. And the answer should be
0.02.
okay, wonderful. So your answer is absolutely correct. So T in this case becomes, so T in this case becomes 0.02 seconds. Okay, can you convert this into milliseconds? Can you convert this into milliseconds? Will somebody convert 0.02 seconds into milliseconds? Very simple. As you replied by virtue of chat,
20.
are you telling me or are you asking me?
Sir, I'm telling.
Okay, okay. See, because you know, from your voice, it appears that as if you are confused and you are clarifying it. Okay. So this is nothing but 20 milliseconds. Absolutely right. So if frequency is 50 hertz, time period time required to complete 1 cycles becomes 0.02 seconds, which is nothing but 20 milliseconds. Okay, great. Now, as we can see that okay, this waveform completes 1 cycle. This waveform completes 1 cycle. Okay, so now this cycle is represented by degrees, which is nothing but 360 degrees. I'm trying to tell you some calculation, and this calculation is very effective. Okay, can I say that when the waveform completes 1 cycle, it undergoes 360 degrees? Am I right? Angle of 360 degrees. Can I say that?
Yes, sir. Yes, sir.
Wonderful, wonderful. Very simple things. Okay. So now I want to write it in this manner. So 20 milliseconds. I'll use the abbreviation 20 ms to 360 degrees. Okay. So therefore 5 milliseconds will correspond to how many degrees?
Ninety.
Okay, give me the answer. So many degrees. How many degrees will be this? 20 milliseconds, 360 degrees, 5 milliseconds.
90 degrees.
Wonderful. Okay, so 90 degrees. Great. Okay, now you have heard that we have got something called a three-phase supply. Okay, three-phase supply. I'll speak about that later on, but I'm sure everybody must have heard there is something called a three-phase supply, and you have seen some very funny things with three-phase supply, especially if you are living in a fairly large apartment. Okay, the state electricity board provides the supply, which is a three-phase supply, and then the houses, they some of the houses are put up on grade phase, some of the houses are put up on one phase, and some of the houses are put up on another phase. Now, sometimes you might have noticed that, out of, let us say, 36 flats, some 12 flats, they do not have electricity, and some remaining 24 flats, they have got electricity. And this is something typically what is called as a single phasing. So out of the three phase, there's a fault with one phase, right? So therefore, those particular blocks of flats, they do not receive electricity, whereas the other flats, mm, normally two-thirds of the buildings, two-thirds of the flats, they get the electricity. Okay. We use something called as three-phase supply for the sake of transmission. Okay. Now these three-phase supplies, the three voltages, I am going to speak about this later on, but since we are about this degrees and second conversion, okay. So these three phases, they differ to each other by 120 degrees. They differ each other by 120 degrees. Okay. Now let us say particular waveform, which was like this. Okay, let us say this was R waveform. Let me say the Y waveform. The Y waveform will be something like this. And let us say the third waveform is a blue waveform. The blue waveform is going to be something like this. Now, this R waveform had the maximum. This R waveform had the maximum value at t is equal to say 5 milliseconds. 5 milliseconds. Okay. My question is that this Y waveform will have the maximum value after how many milliseconds if they differ each other by 120 degrees. You don't answer the question verbally, you have to give the answer in a chat box. You have to answer this question in the chat box. If you are not understood the question, you can unmute and ask. The question is like this: I've got three-phase waveforms. Okay, I've got this three-phase supply, something called as R, Y, and B. Okay, they differ each other by 120 degrees. They differ each other by 120 degrees. I have just shown you the conversion. The supply frequency is 50 hertz. If the supply frequency is 50 hertz, time t will be equal to 20 milliseconds. 20 milliseconds corresponds to 360 degrees. Okay, so therefore, as we did the calculation over here, the 5 milliseconds will correspond to 90 degrees. Now I got three waveforms which are differing each other by 120 degrees. Okay, so a waveform had a maximum value at 5 milliseconds. The second waveform is going to differ it or is going to lag it by 120 degrees. Okay, so my simple question is that what will be the so at what time will this point will come? And you have to answer me by chat. Okay, do not voice out the answer. Type into the chat box. Type the question also into the chat box. So think rationally, very simple question, very simple answer. So think rationally and answer the question. And in the meanwhile, I'm having a look at the attendance also, right? So you keep on, you please think and try and give the answer. And in the meanwhile, I'm taking the attendance. If anybody has a doubt, he or she is absolutely free to unmute and ask. Okay, Indrajit, 76, can you unmute yourself? Indrajit? Okay, I have got some answers. Okay, great. So, yes, I have got the answer from Darshan, right? So, Darshan, your answer is absolutely correct. Dux, no. We are engineers, so we cannot talk like politicians. From between this and this, no. That is not the case, right? So, just substitute into that and answer.
Sir, I have a doubt, sir.
Okay, who is that?
Mr. Darshan.
1 minute.
Sir,
Huh.
sir, in this, how can you compare time here with the angle?
Okay. Very good. This is Darshan 049 only, na?
Yes, sir.
Okay, Darshan, one just small suggestion to you. Your question is very good, but there seems to be some issue with your mic, right? There was a horrible echo when you asked the question.
Okay.
Yeah, that's okay. Absolutely no problem. Right. So I will come to that because I am just what they call as sowing the seeds into your fertile mind, saying that very soon we'll be representing this waveform in the form of a vector. Now you are aware of the vectors.
Yes, sir.
Okay. Now I have got what we are thinking over here is that I have got a vector like this. Now this vector is not a stationary vector, but this is a rotating vector. Now this vector is going to rotate at the angular velocity or at the angular frequency. Okay? And therefore I am able to correlate this time with the degrees. Right? So that's what I wanted to say was that this vector, yeah, Darshan. Okay. So this vector is going to complete just like our frequency. So this vector is going to complete 50 revolutions. Okay, so this vector is also going to make 50 revolutions in 1 second, and one revolution corresponds to 360 degrees. Can you see it, Darshan?
Okay, sir. Understood.
Very good. Okay. Now only 2 of you have attempted it. I'm not really happy with that. Dux, can you unmute yourself? Dux Bharadwaj, 048. Please unmute.
Yes, sir.
Okay. So my apologies, Dux, for publicly correcting you. But since nobody has done that, so please don't take me in a wrong manner. Tell me how you have calculated. You have given me some answer. So please tell me the calculation what you have done.
Sir, like what I did was, see, for the 10 degree, it was for 10 milliseconds, it was 180 degree.
Correct.
And for the 15 millisecond, it was 270 degrees.
Okay.
And it has a difference between of 120 degrees.
Absolutely right.
So for 90 plus 120 is equal to 210.
Okay.
So I was going on that way.
Okay. Right. Now that please remember very simple thing. Okay. The calculation is horribly simple. Okay. So I'll do something like this. So the calculation was something like this. Okay, so our calculation was something like this. So 20 milliseconds means 360 degrees. right? So I have to calculate for 60 degrees. Okay, so 60 degrees means so much. Right, so if this is x, so your x, I have done this in, I think, 7th standard. Okay, so everybody had done this in 7th standard. Okay, so this x will be equal to 60 into 20. Sorry, not 60, not math, 120. Okay, so 120 into 20, 120 into 20 divided by 360, isn't it? Or roughly, this 120 divided by 360 is nothing but 1/3. Okay, so 1/3 of 20. 1/3 of 20, which is nothing but 6.67 milliseconds. Is that okay, Daksh?
Yes, sir.
Okay, so calculation was really simple. Okay, so can somebody tell me, now we were speaking about this particular waveform, yellow waveform. Okay, now if this is 5 millisecond, okay, how much will be this? Now tell me the crisp answer. Okay, this much point, this much millisecond, absolutely crisp answer. Everything is in front of you. All that you have to do is that you have to correlate. Okay, so this is one answer. This is one answer. So how much will be this? So if I'm not mistaken, this is 11.67 millisecond. Okay. So the second waveform, which is a Y waveform, will have its maximum at 11.67 milliseconds or 5.67 milliseconds after the R waveform had the maximum. So if anybody has a doubt, can unmute and ask. Please type into the chat box what we have done so far. Type into the chat box ND2, that means no doubt. Right? Because we had ND many times. What happens is that I go on teaching and there is always ND, so I get mixed up. Yeah, very good. That's right. So we saw some very important concepts, and I tried my level best to teach you those concepts in a very simple manner. All these things that we have learned today are very important. Okay. Today is 28th of February. We had class at 1400 hours. And I think there was only one absentee. Okay, so right now the attendance is 35. Okay.
No, sir, there are 34 in our division.
Correct. No, sometimes what happens is that couple of minutes later, there were 34 present. Right? So including myself, there are 35. So everybody is present. Right? So nobody is absent. All right. So dear guys, this was our first lecture. There are some challenges in online lectures. There are certain advantages in the online lecture. So this is how bad that we will be going to for this course. Right. So anybody wants to give me any feedback or anything you want me to suggest? For example, there was an issue with my voice. You correctly and promptly responded saying that there was my voice was low. So something like that, if you want to do, so please tell me.
So there is a background disturbance.
I know that. Okay.
Sir, there is a lot of distraction.
Okay. What I will do is that whenever I am going to take the lecture from in TMI, I'll identify a classroom, wherein that Wi-Fi router is available, and I will sit over there. when I took the lecture last week, I identified a room, but that room was not having the Wi-Fi router. So my promise is that if I'm taking the lecture from TMI, I'll identify the room and I will sit over there to ensure that there is no background noise. Okay, anything other than that?
No, sir.
Okay, okay. Dhruvo says that 059, sir, whenever you do calculation, please do it on the white background page. I will definitely do that, Dhruvo. Normally, what I do is that I share that whiteboard and I do the calculation over there. I just somehow forgot that. Okay. Otherwise, yes, that is definitely yes. Was the pace okay?
Yes, sir.
Okay, okay, right. So if anybody has a doubt, can unmute and ask. Otherwise, I'll end this lecture. Shall we stop?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Yeah, one more thing. Like last semester, you used to have a break in between of 10 or 15 minutes break in between. Okay. This semester you have got back-to-back lecture, 2 to 3, 3 to 4. So what you did, I mean, what the faculty you did in the last week, the faculty used to walk out and the next faculty used to log, or the first faculty used to end the lecture. What you did last week?
Faculty come.
Okay, because right now, see, for example, I am through with you. Okay, but the next faculty is not there, and I have to, because I am the host, I have to make somebody host. Okay. So that was my question. Is there,
Actually, you can make
okay, whom shall I make host in that case? His number, CR number.
CR, sir.
064.
064. Okay, fair enough. Right. So 064.
So I had unmuted myself.
Okay, great. Yeah. Animesh.
Yes, sir.
So I'll make you host.
Yes, sir.
Right. So I can see you are the host, but for heaven's sake, please make sure that whenever the next faculty comes in, you make him host.
Yes, sir. Yes, sir.
Right. Thank you, guys. Thank you very much.
Thank you, sir.
Yeah.
Thank you, sir.
Jai Hind. I'll leave the meeting. God bless you all.
मीटिंग लीव करने की इसी लिंक पे है
कार ਵਿੱਚ ਯਾਰ
Yeah. Trapness. पाटीदार कहाँ से आता है?
ओए पाटीदार,
बढ़िया सा म्यूजिक चला दो यार।
अरे म्यूट कर रहा है होस्ट, होस्ट म्यूट कर रहा है। ये पाटीदार
भारद्वाज।
भरत देव भारद्वाज।
डिस्को टाइम।
ये
या अभी बजाते रुको।
यस मैम।
ओए लखमेरा, ये चूचा अपने चूना अपने चाचा को लगाना जा।
ये अग्रवाल जो ये काकड़े
मिस्टर हिमांशु अंजना, मिस्टर हिमांशु अंजना, प्लीज अनम्यूट योरसेल्फ।
भारद्वाज, where are you?
Cadet, mute yourself. Okay.
Mute yourself. The teacher has come. Yes, yes.
Dhruv.
Dhruv Kakade, mute yourself.
Okay. Mute yourself. Dhruv. Okay. You are enjoying music and all. Definitely no problem at all. But not here like this. Okay.
Good afternoon, sir.
Good afternoon. Good afternoon.
Afternoon, sir.
Good afternoon. Right. Good afternoon. Right. So just a minute, cadets. Wait for a minute. Wait for 2 minutes, cadets, because actually just lecture finished and I will start this. Okay, so wait for 2 minutes.
Okay, sir, no problem.
Okay, sir.
Okay. Good afternoon, cadets.
Good afternoon, sir.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon to all. Okay. So just a minute. First of all, okay. Division 2. All right. So, okay. What about your CR now? Prathamesh or Animesh?
Prathamesh Jadhav, sir.
Prathamesh Jadhav. Okay. Okay. So, Prathamesh, you just okay. After this lecture, that is apartments. All of you knows about that one, right? So, division 2. Okay. Right. So let's start today. Okay. The last lecture. Okay. You just give me some answers. Not answers. You just give me some something about means what you had already done in the last lecture. Last lecture part. Anybody knows? Anybody? Just 2 minutes revision, not revision. That is just like what things you've done in the last lecture. Yes, anybody? अरे अभी तो म्यूजिक चल रहा था बढ़िया ध्रुव
सर वो किया था हमने कन्वर्जेंस बाइनरी डेसिमल में
Oh, no problem. Okay, you are talking about digital electronics. Okay, by Abraham, sir. All right. Okay. That is again a confusion. The last lecture, Abraham sir lecture, and then again my lecture is there like that. Okay.
Yes, sir. आपने सेमीकंडक्टर पढ़ा है.
Semiconductor. Okay. Right. So see, cadets, and I know about this type of confusion again because I'm talking about semiconductor. Abras are talking about some digital electronics like that. So because of that, from this week, your timetable is like this. Means Monday, Tuesday, Wednesday, Thursday. Means total 3 lectures are there in a week. Okay, so 2 lectures. I will conduct 2 lectures, and Abra sir will conduct only 1 lecture in that week. And in the next week, I will conduct only 1 lecture and 2 lectures for Abra sir. That means some type of flow is there. Okay, means what we are talking because electronics subject is there and so many things are there. So definitely that type of confusion is there, right? Okay, so this type of arrangement done here. So one thing for you, right? Because as per the year coordinator, what stationery is required. So in that stationery, I had already recommended one 200-page book, 200-page book for electronics, right? So I don't know about Abrar, means what he is explaining, or if you want to write anything, or if any type of numerical is there in digital electronic or whatever the design is there. Okay, that is up to you. If you want to note down anything, then you just note down and see in that 200-page book, you just divide that book in 2 parts, 100-page for me and 100-page for Abrar, right? That is totally depend up to you, right? Because if you want to write anything, that book is given, right? Okay, but my suggestion is in my lecture you don't write anything. Okay, you don't write anything because you just concentrate what I'm talking. Okay, because everything is given in my notes. Okay, because I will clear detailed notes for your study. Okay, detailed notes. Okay, because the book is given, but that book size is this much, means so many pages are there. But again, one thing for your information, book is given, so you just read that book at least once, and refer my notes again and again. Okay, are you getting refer
Yes,
that
sir.
book at least once, because that book is a very very means so many things are given in that book, and the teaching from that book means each and every point that is not possible in my lecture, right? Definitely according to syllabus I will cover each and every point, but so many things are written in that book, right? So just once, okay, just once you read that book carefully. Okay. Okay, so this is from my side, because again means after exam and all, you can say means सर आपने तो इतना ही बोला था, आपने बोला था हम लोगों को कि बाकी कुछ नहीं पढ़ना है, ओनली नोट्स आर the okay, notes में सब मिलेगा, my notes are means that type of notes are there, but at least once, right? Okay, right. So let's start in the next sorry, not next, next time I will go for the advanced part, but today again we will discuss something about semiconductor, right? Because in the last lecture the I think sorry, in the last lecture the semiconductor, intrinsic semiconductor, extrinsic semiconductor, doping, n type, p type semiconductor, that part done, right? So now the next part here is what, see, I will share my slide here first, just a minute. Okay, your division strength is 35, right?
34.
34.
Yes, sir. 34.
Confirm. So here 36 are present, including me. Including me, here 36 are there. Participants are 36. I don't have any objection if any other candidate is there, but CR, you just go through this one, because total 36 are here now.
Dhruvo is having logged with 2 IDs. Login with
Okay, no problem. Right. Okay, so I will share slide here now. Okay. So, again, the topic is same. That is basic electronics, semiconductor theory. As per syllabus, as per CHLP, the point written is majority and minority carriers. Okay, majority and minority carriers. Okay, what is this majority and minority carriers? Means what? You know, n-type semiconductor, p-type semiconductor. Okay, so what is majority and minority carrier in p-type semiconductor and n-type semiconductor?
Holes and electrons.
Then electrons.
Okay, but in n-type semiconductor, the majority carriers are holes or electrons?
Electrons.
Electrons. N-type electrons, p-type holes.
Okay, n-type semiconductor, then the electrons are majority carriers, and in p-type holes are majority carriers. Okay, yes. Very good. Okay, very good. See here now. The charge carriers that present in large quantity are called majority charge carriers. The majority charge carriers carry most of the electric charge or electric current in the semiconductor. That means actual current flowing through that semiconductor is because of majority carrier. Hence, majority charge carriers are mainly responsible for electric current flow in the semiconductor. Because of majority carrier, current will flow through that semiconductor. Yes, definitely, because of minority carrier, some current will flow, but the majority carriers are important part here. Right? Okay. So, okay. The charge carriers that are present in small quantity are called minority carriers, minority charge carriers. The minority charge carriers carry very small amount of electric charge or electric current in the semiconductor, right? Okay, so majority charge carriers and minority charge carriers, or majority carriers, minority carriers, this point is mentioned in your syllabus. So because of that, concentrate here. Okay. The large number of quantity are called majority carriers, majority charge carriers, and small quantity. Okay. The charge carriers that are present in small quantity are known as minority charge carriers. Right? This one. See here in p-type semiconductor, the majority charge carriers are holes. These are the holes, and the free electrons are minority charge carriers or minority carriers, whatever. Okay, free electrons are less number of free electrons are there, and holes are this much. Okay, so because of that, the majority charge carriers are holes. And in n-type semiconductor, free electrons are majority charge carriers or majority carriers, and holes are minority carriers. Right? Okay. Okay. Now your answer. Okay, because already asked about this one. Charge on n-type and p-type semiconductor. See, due to thermal energy, still hole electron pairs are generated, but the number of holes are very large compared to the number of electrons. Therefore, in p-type semiconductor, holes are majority carriers. In p-type semiconductor, holes are majority carriers and electrons are minority carriers. Since the current conduction is predominantly by hole, that is positive charges, it is called a p-type semiconductor. P means positive. This is only for your information, cadet. You don't write like this. P means positive. Okay, P means positive. This is actually this type of theory is not there in electronics. P means positive, N means negative, like that. Okay, P means the p-type semiconductor and N means n-type semiconductor, but this is only for your information, right? So hole or the positive charge is there, that is a majority charge on p-type semiconductor. So due to thermal energy, same thing, still hole electron pairs are generated, but the number of free electrons are very large in number when compared to holes. So in an n-type conductor, electrons are majority charge carriers and holes are minority charge carriers. Again, since the current conduction is predominantly by free electrons, that is negatively charges. See here, this is positive charges, negatively charges or negative charges. It is called n-type semiconductor. N means negative. This is for your info again. Okay, in your paper you don't write like this. Actually this is correct, but don't write like this. N means negative, P means positive, like that. Okay, if it is written, then examiner will consider that part, but that is not actual theory, right? Okay. So charge on n-type and p-type semiconductor, right? The next point is what? Negative charge carriers. Just go through this one. Same thing is written here. The negative charge carriers such as free electrons are the charge carriers that carry negative charge with them while moving from one place to another place. That means because of thermal energy, the electrons are moving in the orbit, right? So that electrons carry negative charge with them while moving from one place to another place. That is what? That is negative charge carriers. Free electrons are the electrons that are detached from the parent atom and moves freely from one place to another place. Okay, I think free electron and valence electron, this point is clear to all, right? Valence electrons in germanium or in silicon, 4 valence electrons are there. Free electrons means what? Because of thermal energy, that electrons becomes free electrons, right? Free electrons and the electrons that are detached, free electrons are the electrons that are detached from parent atom and moves freely from one place to another place. This point is clear, cadets, right? Okay. Now positive charge carriers. Positive charge carrier means what? If free electron is there, obviously vacancy creation is there, and that vacancy means hole. That is positive charge carriers. See here now. The positive charge carriers such as holes are the charge carriers that carry positive charge with them while moving from one place to another place. Okay, so holes means positive charge. If holes are moving, that holes carry means they will carry positive charge when they are moving from one place to another place. Holes are the vacancies in valence band. See here, because of free electrons in that valence band, vacancy creation is there, and that vacancy means what? Holes are the vacancies in valence band. Okay, and these electrons goes outside from that valence band. These points are very important, cadets. Maybe this type of MCQ type questions are there. Okay, so because of that, read these things very carefully, right? Holes are vacancies in valence band that moves from one place to another place within the valence band. Within the valence band. Okay, these things are very important, cadets. So because of that, whatever the points written here, go through that points carefully. Okay, because definitely in MCQ type question, that is again confusing. Okay, means whatever the question asked here, you just think about that question twice, and according to that you select your actual means the correct answer, right? Okay, because maybe again next time same type of exam is there, again MCQs are there. Okay, so because of that I'm talking like this, means you just prepare yourself for this type of questions also, right? Okay, then what is mobility? Okay, this point is mentioned in your syllabus again. What is mobility? Okay, any idea what is mobility? Yes, cadets.
Stable.
Okay, no problem. See, mobility in a semiconductor is defined as how speedily charged carriers like electrons move in a semiconductor. Okay, not only electrons, holes also. Okay, so hole mobility and electron mobility, both type of mobility is there. Okay, but that things are not included in these slides, but in my notes I will add that part also, right? But what is mobility? The mobility in a semiconductor is defined as how speedily charged carriers like electrons move in a semiconductor, right? Okay, the measurement, sorry, just the measurement of how fast an electron can move through a semiconductor or a metal which is under the influence of an external electric field is known as electron mobility. Obviously, external electric field is required, then only electrons will move. We can show electron mobility mathematically by the equation mu is equal to VDE. Okay, what is this VDE? See here now. The mobility mu is defined as magnitude of drift velocity. Okay, now what is drift? Okay, drift current and diffusion current is there. I will explain that part also. Okay, so the mobility mu is defined as the magnitude of drift velocity per unit electric field. So this one is this one, E mod of VD. This one is what? Drift velocity per electric field. This is a mobility. Mobility is denoted by mu. So just clear this point. Mobility is mu. Mu is equal to E into VD or VDE, whatever. Okay, VDE or EVD, that is same, right? Okay, this is a mobility. Okay. Now, the next and important part as per your syllabus. Okay, again, what I'm talking, as per your syllabus, one point is written. That point is hole current. Okay. Now, you tell me what is hole current and what is electron current. Is there any difference? Hole current or electron current? This is a diagram now. Okay, this is a diagram here. Okay, this one is a germanium. This one is germanium semiconductor. Okay. So anything is there, hole current and electron current. Electron current means what? And hole current means what? Okay. See here. Current that is caused by electron motion. Okay. Current that is caused by electron motion is called electron current, and current that is caused by hole motion is called hole current. Okay. So as means according to this diagram, you got anything about hole current? What is this diagram? Means, from this diagram, what thing is means what is the given in this diagram? Yes, cadets. What is this? Are you listening this one? Means what I'm talking?
Yes, sir.
Yes, sir.
Right. So what is given in this diagram? Any idea about this diagram?
So are the hose moving from one band to another to carry current?
Very good, very good. See here, actually in this diagram, what is mentioned? See, every time because of thermal energy, four valence electrons are there. And because of thermal energy, here you just consider one free electron is there. So because of that, vacancy creation is there. Suppose again here, because of thermal energy, again free electron is there. So again vacancy creation is there. Again free electron is there, again vacancy creation is there. Again free electron is there, again vacancy creation is there. So that is given here L, M, N, P, Q, like that. Okay, so according to that, from positive terminal of battery, holes are moving towards negative terminal of battery, right? Negative terminal of battery. So this current is conventional current or actual current, cadets? This current is conventional current or actual current?
Actual.
Actual
current.
पक्का?
सर कन्वेंशनल तो प्लस से माइनस में था.
हाँ तो पर यहाँ पे प्लस टू माइनस ही जा रहा है ना, वही तो मैं बोल रहा हूँ. दिस इज प्लस, राइट? दिस इज गोइंग फ्रॉम plus to minus, right? So yes. This is a conventional current, right? Okay, no problem. Okay, so this is a conventional current. So obviously hole current is a conventional current and electron current is actual current, right? So as per semiconductor theory, electrons are moving from negative terminal to positive terminal, and as per conventional theory, the holes are moving from positive terminal to negative terminal. Holes means same, means the current flowing from positive terminal to negative terminal. This is the main concept of hole current. See here now. I will show you that point also. Just a minute. See here. The electric currents, again hole current is written here. The electric current that flows from positive terminal of battery to negative terminal of battery is called conventional current, right? Positive terminal of battery to negative terminal of battery is called conventional current. The conventional current direction is in the same direction of flow of holes, right? But opposite to direction of flow of free electrons, right? From this point, I think this explanation is clear now, right? So positive terminal of battery to negative terminal of battery, that means movement of hole is like this. Okay, so flow of holes is this one and flow of electron is this one. So flow of electron means actually according to the electron theory, the current is like this, and according to conventional theory, current is like this. So conventional current means hole current. Again, MCQ type question. Okay, so hole current is conventional current or electron current, like that, or whatever the things are there according to that. Okay, so hole current is a conventional current. Just remember this point, right? Hole current is flowing from positive terminal of battery to negative terminal of battery, right? Clear this point? Okay.
Yes.
Okay. Yes, sir. Then the next point written is diffusion current. See, Actually, this diffusion current, drift current, hole current, electron current, whatever the currents are there, okay, whatever the currents are there, the meaning is same. Again, meaning is same. Because of that current, that semiconductor device goes in on state, off state, like that. Okay. So diffusion current. Diffusion current means what? What is diffusion? See here. The process by which charge carriers means what? Electrons or holes in a semiconductor moves from a region of higher concentration to a region of lower concentration is called diffusion. Okay, see here. The process by which charge carriers, electrons or holes in a semiconductor moves from a region of higher concentration to region of lower concentration is called diffusion. The region in which more number of electrons is present is called higher concentration region. Obviously, more number of electrons are present, that means that is more concentration, or higher concentration region. And the region in which less number of electrons is present, it is called as lower concentration region. The current, see here, this is your answer now. What is diffusion current? The current produced due to motion of charge carriers from a region of higher concentration to a region of lower concentration is called diffusion current. Current produced due to motion of charge carriers. Motion of charge carrier is important here. From a region of higher concentration to a region of lower concentration is called diffusion current. Right? See here now. This one is a higher concentration region. This one is a higher concentration region. And this one is a lower concentration region. Okay. You can consider hole or electron, whatever is there. But here it is given electron. So this is electron. No problem at all. Right? So diffusion of electron. What is this diffusion of electrons here? This is non-uniform concentration of electron. Okay. Because this one is higher concentration. This one is a lower concentration. So obviously higher concentration region moves towards lower concentration region. So the current direction means what? These electrons are moving like this. Okay. So this is a uniform concentration of electrons. This is a uniform concentration of electrons. These electrons are like this now. Okay. Because of movement of the higher concentration region electrons to lower concentration region of semiconductor. Right. So this is a diffusion of electrons and this is a diffusion current. This point is clear, cadets?
Yes, sir.
Right. Very good. Okay. You ask any question, any silly question also. Right. Okay. Right. Okay. Now, silly question means what? You have whatever the queries are there, ask on that time. Right. Drift current. Now, drift current is very easy. All of you knows about this one. If this battery is connected, then obviously flow of electrons, flow of holes and flow of electrons is there. That is known as drift current. See, the flow of charge carriers, which is due to applied voltage or electric field, is called drift current. So this is our general statement. This is our general statement. The flow of charge carriers, which is due to applied voltage or electric field, is called drift current. In a semiconductor, there are two types of charge carriers. They are electrons and holes. When the voltage is applied to a silicon, the free electrons move towards positive terminal of battery and holes move towards negative terminal of battery. This concept already explained in previous slides, right? So the voltage applied, that means the free electrons move towards positive. Free electrons means what? This one. See, free electrons move towards positive terminal and the holes moves from positive terminal of battery to negative terminal of battery. Right? So this is a drift current. See here. What is drift and diffusion current? Both drift and diffusion current occurs in semiconductor devices. Diffusion current occurs without an external voltage or electric field applied because higher concentration to lower concentration. So that is occurred in semiconductor without any external voltage or electric field, right? The diffusion current does not occur in a conductor. Yes, definitely. Diffusion current is not there in conductor. Right? Because conductor is something different. In conductor, the conduction band, valence band, both are same. Okay, both are same. But in semiconductor, diffusion is there because from valence band, the electrons are moving towards concentration band, or the more concentration and less concentration is there. So because of that, diffusion is there in the semiconductor. So diffusion current does not occur in conductor. The direction of diffusion current is same or opposite to that of drift current. That is totally depend again. Okay, the direction of diffusion current is same or opposite to that of drift current. Drift current means positive to negative, negative to positive. That is according to theory. Right? So this is a drift current and diffusion current. Definitely so many things are there, cadets. I will add that things in my notes. Okay, so many things are there. I will definitely add all these things in my notes. Right? But this is the concept of that. The concept is clear, cadets? Okay, I think clear, because there is no any answer. So that means I think the concept is clear, right? Okay. Okay. So the next point here is a PN junction. PN junction. Okay, now you tell me something about PN junction. What is PN junction? PN junction means what? Yes, cadets. What is PN junction?
The junction between positive and negative type semiconductor.
Okay, junction between positive and negative type semiconductor. Very good. Your answer is same. You're right. Okay, no problem. See here now. When a p-type semiconductor is suitably joined, see here, suitably joined. This is very important point, cadets. Okay. Okay. When a p-type semiconductor is suitably joined to n-type semiconductor, the contact surface is called PN junction. Suitably joined means what? See here. That is depend on concentration of that joining. The depletion region will form in between p and n type semiconductor. So because of that, this is written here, suitably joined to n type semiconductor. Otherwise this is not this point is not there. Okay, see, when a p-type semiconductor is joined to n-type semiconductor, okay, just joining is there. So because of that, one surface is contact surface is there. That contact surface is called as PN junction. Okay, that is the PN junction. Okay, see here now. This one is a p-type silicon or germanium, whatever. Okay, this one is n-type silicon or germanium material, and these two materials are connected or joined with each other. So because of that, this contact surface formed, that surface is known as PN junction. Okay, or that contact is known as PN junction. Okay, so again, cadets, PN junction diode, crystal diode, whatever written in different textbooks or reference books, the meaning is same, cadets. Okay, PN junction means PN junction diode. That means crystal diode. The meaning is same. This is just like a diode, because P and N type semiconductor is connected to each other. That means this contact surface is known as PN junction, or this device is known as PN junction diode. PN junction diode. If the doping, not doping actually, the according to concentration, suitably joined, the barrier voltage is totally depend again which type of material is used. So here, see here now, p-type semiconductor region here, that means holes are there. N-type semiconductor region is there, that means electrons are there. Definitely this is majority charge carrier. This one is a majority charge carrier in p-type semiconductor is hole. Majority charge carrier in n-type semiconductor is electron. right? See, the combining of electrons and holes depletes the holes in the p region. Okay, depletes the holes. See here, depletes the holes in p region and the electrons in n region. See here, depletes. Okay, so because of that, near this junction, one region formed, and that region is known as depletion region or depletion area, or whatever the things are there, or sometime it is known as barrier region. Okay, or depletion area, whatever. Okay, that is totally depend on that author. Okay, so this region, because of this junction formation, this region creation is there, that is known as depletion region, right? See, this one is the electron, this one is a hole, this one, see here, this one here. Okay, this one is what? Combination of hole and electron, so because of that, this is known as means this is what? Negative ion from filled hole, negative ion from filled hole, right? Here, this one is a positive ion from a removed electron, because these electrons goes to this one. Because of that, holes goes here, right? So this one is a positive ion from removed electron. Electrons are not there in this area, so because of that, this positive ion formation is there near this junction, right? So this total junction, this region is known as depletion region. Clear this point, cadets, what I'm talking?
Yes, sir.
Right? Okay. So the PN junction diode. Okay. What is this? Diode is an electronic device which allow current to flow in one direction only. Okay. This is again an MCQ type question, cadets. Okay. PN junction diode allow current in both direction. Okay. Yes or no? No. Obviously no. Because current flowing through that diode in one direction only. Because in forward bias only current will flow through diode. Not in reverse bias. That means anode to cathode current will flow through that diode. That means P type. Okay, that is the next part. Okay, I will not explain that part here. Okay, so the current flowing through that diode is in one direction only. The voltage applied to the semiconductor diode is referred to as bias voltage. So obviously you have to apply the required voltage. Required voltage means what? Again, see, not actually required voltage, the proper voltage. Okay, that means proper positive terminal, proper negative terminal is connected to proper anode and cathode terminal of diode, then only current will flow through that diode. Okay, that is a biasing. This bias voltage, this point is very, very important, cadets, because this biasing is there in diode, in transistor, and then FET, MOSFET. So many things are there in your syllabus. So biasing voltage means what? They actually, to conduct that particular device, to switch on that particular device, you have to apply a voltage. That is known as bias voltage. Okay, so that means if you want to amplify any AC signal, so that AC signal is not a biasing voltage. Okay, to switch on that transistor or to switch on that particular device, you have to apply some voltage. That voltage is known as bias voltage. That is our next part. Don't bother about that. But this is important point here. The voltage applied to semiconductor diode is referred to as bias voltage. Okay. This one is a symbol of PN junction diode. And you draw this symbol of diode very carefully in your exam. Okay, because so many times this is my observation. So because of that, I will explain something like this. So many times the symbol of diode in exam is like this. 0 marks for this. Okay, this is not a diode. Okay, your concept is what? Current flowing in one direction, so because of that one arrow is there. No, this is wrong. This is wrong. Okay, so don't do like this. If your question is for 1 mark or 2 mark, because in IMU exam this type of questions are there, cadets. Okay, draw a symbol of diode. So this is not a correct symbol for that. Okay, that examiner will give you 0 mark in that case. Okay, this is a proper symbol. Okay, so this line is important here. Again, this line means cathode. This line indicates cathode, and this arrow head indicates anode. Arrowhead indicates anode. Right, so this is a proper symbol here. You have to draw a proper symbol of p-n junction diode. Right, cadets? Okay. Okay. See here, this one is a diode. This one is a diode. I think means if you aware of this one, this diode, then the diode looks like this. Okay, one lead is there. This is a anode. This one is a cathode. See here, on this diode, this anode and cathode not written anywhere. Okay, the diode looks like this. That means this ring, this silver color ring or golden color, not golden color, silver color or glass type of diode is there, then black color ring is there. So this ring means cathode. Ring means cathode. So obviously this terminal is a cathode and the opposite terminal is anode. This is an indication on this diode, actual diode, right? So many numbers are written, 1N5001, 1N1001, like that. That is according to datasheet, everything is there. Okay, current rating, voltage rating, whatever the things are there. Okay, so that you have to, in that case, you have to refer datasheet of that diode. Okay, that is also mentioned in your syllabus. So because of that, what is datasheet? What is number of diode? Okay, so you have to refer all these things, cadets. Okay, your syllabus is very vast. Okay, again I am saying syllabus is very vast. So you just start your study from first day. Okay, from first day. Okay, right. So this is a ring here. This ring is known as cathode. Ring means cathode, and this another terminal is anode. Right. Then the last part of our today's lecture, okay, that is properties of p-n junction. So properties of p-n junction. Okay, this is very easy part because you know p-n junction formation and the terminals are there, depletion region is there. So that is written in this properties of p-n junction. Yes.
Sir, I had a doubt regarding the forward and reverse bias. Sir, you said कि reverse bias में current नहीं flow करता, but sir there is a concept वो नहीं होता breakdown voltage.
Okay, current flow करता है सी, लेकिन वो current जो है वो हम लोग use नहीं कर सकते.
Sir वही नंबर करता तो
हाँ करता है, लेकिन एक पर्टिकुलर पॉइंट पे जब करंट वहां पे आएगा ना, वो डायोड बर्न आउट हो जाता है, मींस डायोड जल जाता है, राइट. इसलिए हम लोग बोलते हैं कि डायोड वन डायरेक्शन में ही काम करता है, राइट. दैट इज द रीजन. एक्चुअली करंट फ्लो होता है, डेफिनेटली करंट फ्लो होता है, दैट इज रिवर्स करंट, लेकिन रिवर्स करंट हम लोग कहीं पे यूज नहीं कर सकते. ओके, क्योंकि रिवर्स बायस में हम लोग कभी डायोड को नहीं चलाते. ओके, रिवर्स करंट फ्लो होता है, उसके लिए भी एक रीजन है, वो हम लोग रेक्टिफायर में देखेंगे. ओके, क्योंकि रेक्टिफायर है हमारे सिलेबस में, तब मैं एक्सप्लेन करूंगा कि रिवर्स बायस में उतना लीकेज करंट वहां पे क्यों चाहिए. ओके, क्योंकि उसमें से रिवर्स करंट भी रेक्टिफायर में फ्लो होता है, उसके लिए रिवर्स कैरेक्टरिस्टिक उसकी थोड़ी सी अलग है, तो उस टाइम पे मैं बता दूंगा डेफिनेटली, राइट. बट दिस इज अ यूनिडायरेक्शनल, right? Okay, your question is correct, and your concept is means you know very well about that one, but that is not in use, right? Okay, right. So properties of p-n junction. At the instant of p-n junction formation, the free electrons near the junction in the n region begin to diffuse across the junction into the p region, where they combine with holes near the junction. Okay, one line is written here. Okay, not a difficult part here. Free electrons from n-type semiconductor goes to p-type semiconductor. Okay, that means diffusion across the junction into the p region where they combine with holes near the junction. That part already explained in the previous line. Okay, that means p-n junction formation is there. So because of that, recombination takes place, right? That means diffusion, right? The result is that n region loses free electrons as they diffuse into the junction, right? N region loses free electrons as they diffuse into the junction. This creates a layer of positive charges, that means pentavalent ions near the junction. Okay, in n region, and same thing here. As the electrons move across the junction, the p region loses holes as the electrons and holes recombine or combine. Okay, electrons and hole combine. The result is that there is a layer of negative charges, that is trivalent ions near the junction. That means positive as well as negative, that type of layer is there near the p-n junction, right? And that layer is known as depletion layer, right? Okay, see here. These two layers of positive and negative charges form the depletion region or depletion layer. Same, depletion region, depletion layer, barrier region. The meaning is same, cadets. Okay, that is again up to the author to author. The words are something different. Okay, depletion layer, depletion region, barrier region, everything is same. The term depletion is due to the fact that near the junction the region is depleted. That means emptied. Okay, of charge carriers, free electrons and holes. Okay, due to diffusion across the junction. Yes, definitely, this is because of diffusion across the junction, right? That is depletion layer, right? The depletion layer is formed very quickly and is very thin compared to the n region and p region, right? N region and p region, but that the junction, because of this junction, one depletion layer formed, and that is very thin as compared to the n and p region used in that junction. Potential difference across the depletion layer is called barrier potential. VO, V0, kabhi bolte V0 bolte, kabhi VO bolte. That is same. Sometime author will say VB also. VB means barrier potential. Okay, the meaning is same again. Okay, because in your exam also, barrier potential, depletion potential. Depletion potential is not there. Actually, the correct word is barrier potential, but it is represented by VO, V0, or sometimes VB also. VB means barrier potential. Okay, the potential difference across the depletion layer is called barrier potential, PN. Right? The barrier potential of PN junction depends upon several factors, including the type of semiconductor material. The amount of doping, and temperature. Okay, so this barrier potential is totally depend on these factors. Okay, the amount of doping and temperature, because already this point discussed in this previous slide, that is because of that concentration. Okay, that means doping and temperature, as well as semiconductor material. That barrier potential is totally depend on these factors, right? So in our last lecture, this point already discussed. Okay, the band gap of the semiconductor is about 1 eV, and that band gap is 0.7 in germanium and 1.1 eV in silicon, right? The meaning of that point is what? This one, see here. The typical barrier potential is approximately, for silicon, VB or VO is 0.7 volt, and for germanium, this VO or VB is 0.3 volt. Okay, the energy gap, that band gap in this germanium is 0.7, right? So 0.3 volt is sufficient to break the junction, okay, semiconductor junction. And for silicon, it is 1.1 EV. That means something more than this. Something more than this means what? 0.7 volt is required to break the barrier region or the depletion region. So because of that, for silicon, VB is 0.7 volt, and for germanium, VB is 0.3 volt. Right? These points are clear, cadets?
Yes, sir.
Right.
Yes,
Okay. Okay. So here we will close our meeting. Okay, because
Hey
again,
Siri, what is the
Sir?
time?
yes,
Sir.
yes.
Sir, how barrier potential is calculated?
It's 3:57 p.m.
Hello. Just a minute. Yes.
How barrier potential is calculated?
Barrier potential calculation. Okay, calculation is totally depend on this one. See, basically, if silicon diode is there, then barrier potential is 0.7 volt. Again, see here. Again, if the mass production is there, then the ideal value for silicon diode is 0.7 volt. Okay, but some diode value is 0.6 or 0.55, 0.58, 60, 62, 0.7, 0.72. That is totally depend on the doping and temperature used in that case. Right? Is it clear now?
Okay, sir.
Okay, that is not fixed, but the ideal value for silicon is 0.7 volt. But that diode means if you are using so many diodes, so one diode is conducting at 0.67 volt or 0.68 volt or 0.65 volt. That is totally depend on the amount of doping as well as temperature and the semiconductor material also. So there is no any calculation. Actually, calculation means what? This type of calculation is there. That is not a calculation, right? That is a barrier potential. That means in theoretically we are referring silicon means 0.7 and germanium means 0.3. Right, cadets?
Okay, sir.
Okay. Again, there are so many things, but that is not required. Okay, that is not required. Right. Okay. So the attendance is what? All present here now?
All
Yes,
present.
sir.
Okay.
All present.
All present. Very good.
Thank
very
you,
good.
sir.
Okay. Again, this is a reminder for you. Create one WhatsApp group. So that is very easy for communication. Okay. Create one WhatsApp group, and I will share so many things on that WhatsApp group. Right?
Okay, sir.
Okay,
CR
sir.
will make.
Yes. CR will. Okay. Bye. Bye. Sir, can you please provide syllabus in Moodle? Yes, definitely. I will upload all these things.
Yes, sir. CHLP.
Yes, CHLP also. Right. Okay. Right. Bye. Take care.
Thank you, sir.
Thank you, sir.
Jai Hind, sir.
Thank you so much, sir.
Vande Mataram, sir.
Jai Hind, Vande Mataram.
Vande Mataram.
Bye.
Jai Hind, sir.
Sir.
Next faculty is present here, or can I?
Sir, make sir CR host.
Okay. CR तू कहाँ दिख रहा है मुझे? Okay, Anand Pandey is there. Anand Pandey.
Anand Pandey sir is there.
Right. I will make him host. No problem. Okay, sir. You are host now.
Thank you very much.
Okay.
Thanks a lot.
Bye.
Bye. Good afternoon, Division 2.
Good evening, sir.
Sir.
Afternoon, sir.
Good afternoon.
Good evening, sir. Good evening, sir.
Prathamesh, Harsh, Animesh.
Yes, sir.
I think I met you in the workshop today. Yeah, good.
Yes, sir.
Some of you, yeah. Good. Now, take a break for 3 to 4 minutes. Drink water, etc. And get ready. We'll begin.
Yes, sir. Thank you, sir.
Engineering mechanics. Okay.
Thank you, sir.
अरे हर्ष यादव तू तेरा ये पिक्चर बदल तेरा मुंह दिखा इधर कैंपस नहीं देखना है हमें 8071 Fine. Good afternoon, everybody. We are 34 cadets present, and that looks very nice. Almost 100% attendance. And here we begin. I hope everybody is back in front of a laptop and are listening to me. Bharadwaj, are you here?
Yes, sir.
Oh, yeah, very good.
Yes, sir.
I'm delighted.
Yes, sir.
Yes, Ekta. Fine, good. Our today's topic is, we want to understand two things. First, a free body diagram, and a second, a support reaction. They have a connection with each other, and I'll explain you how does it go. Let us take our screen share so that we can further work into it. This is how we will be going. This is our week 2, 20th February to 5th March. And this PPT will be developed throughout the week, and on the Saturday, it will be sent to you in a PDF form. So you can, of course, make your own notes also parallelly. And whenever a question comes, you ask me a question straight away in a chat box only. I always save a chat box so that I can make a necessary changes into my slides so that finally material that reaches you is a straight away useful. Okay. Now, syllabus is vectors and the scalars and some many other things. Law, parallelogram of the forces, triangle of forces, polygon of forces, condition of equilibrium and everything. What is the moment, effects of a moment, etc. But from here, things start becoming interesting, and that is a determined support reactions. And before that, there is a free body diagram. What are support reactions? See, on any structure, be it a simple beam or say, let it is a large bridge with a supported at this point, supported at this point, supported at this point, over here, etc., etc. This bridge has a loads on it. Some loads are very obvious. A truck over here, another truck over here, a car over here, another car over here, etc. We can say all those loads are acting over here. These are the force very exactly can be judged and located. These forces are, we know this can be a 20 kilonewton, this can be another 22 kilonewton, this can be a 10 kilonewton, this can be another 10 kilonewton, etc. Okay. Now, these forces can be seen. There is one more obvious force. Say suppose here is a center of mass of a bridge then there is its weight acting downward. Its weight is acting downward over here, whatever. Then there are some other forces acting also. Why? Because sum of all the forces, all these forces are acting downward. So there is a net very large force in a negative y direction. But for this bridge beam to be in equilibrium, that is for it to not even get accelerated or displaced, net force on this should be 0. So this beam must be having a upward forces acting also. From where does the upward forces come? Those upward forces will appear at a support reaction. This support will give a upward force. This support will get upward force. This will give a support upward force. Upward. Now once we have knowledge of all the forces, we got to draw a free body diagram. What is a free body diagram? In a free body diagram, we show a body of our interest and remove all other material bodies, but not forces. We will say here weight W is acting. Here 10 kilonewton is acting, 10 kilonewton is acting, 22 kilonewton is acting, and 20 kilonewton is acting. All are shown, and we also show a reaction upward, reaction upward, reaction upward, upward reaction, and an upward reaction. We are showing only forces acting upon a body. Apart from this, there is no other force acting on the beam. Beam is represented free from any other mass and only has its own forces. That is called a free body diagram. Free body diagram for a different beams or a different trusses or different structures will be always different because they will be different loads. It can be very well appreciated, but what is important is how to find a support reaction. Now, if this is a beam which is just resting upon two support, between two support, just placed over there, This place is a frictionless, it cannot offer any resistance. Then, if it is subjected to any amount of a forces, this support and this support being simple, they will permit a deformation like this. This support also permits a movement in a x direction, but this support does not permit in a y direction. That means this support can give a reaction in a y direction only. If you have any curiosity, you can stop me. Any confusion?
Yes, sir. Can you repeat this part again?
Okay. Very good. I thank you, cadet, for asking me a question. This is a beam. Say it is just resting, say, on a roller like this. Now, if you give a load in this fashion, then the beam may take, say, this kind of a shape. Agreed?
Yes, sir.
Look, the support over here has permitted a beam to rotate. Rotate in a sense, this line was straight, now it has become curved over here. If I take a center line of a beam like this, that has become a center line like this now. So this red line in this particular place is, it was like this, so it rotated by this much angle. Here also it is rotated by this much angle. Okay. So beam could rotate at the support. Plus beam can permit a movement in x direction on a roller because there is no friction over here. But this support will not permit a movement in a downward direction. So it can also give a force in upward direction. Beam is rotating because there is no moment over here to resist the rotation. Beam is moving in x direction because there is no force in a x direction. But beam has a resistance in a going down because this support will not let the beam go down. It can happen only if this support is capacity enough to push the beam up. Do you get it now?
Yes, sir. Thank you.
As a result, such roller support, wherever they give only a upward force. Nothing beyond that. Now, there can be another support. Just watch it. that support is like this. Here there is a beam, and we take a hinge. There is a hole over there, and here there is a plate like this. And this is fixed. Now, if force acts upon the beam can freely rotate. Suppose it has a similar kind of a support here also, let us assume. This hinge is fixed, this hinge is on the roller. Now, if you give a load, then this beam can deflect in this fashion. Okay. There is a hinge, so rotation is permitted, so there is no resistance. There is no moment like this. No. This point cannot go in a x or a y direction, so there will be a reaction in this direction. This hinge will oppose. If somebody tries to push the beam this way, this pin will push the beam back. Again, if any system of forces try to push the beam upward, then this pin will resist it also and bring it down. Same way, any system of forces, if tries to push the beam down, beam will push the pin up also. As a result, schematically, at this point, there can be a support reaction in a x direction and a support reaction in a y direction. Excuse me, y direction. Here, this support is on the roller. As a result, any force trying to push the beam left or a right, this roller can move. So this particular support will not give any resistance. If beam wants to rotate, this hinge will permit it. So there will not be any resistive couple. So this support cannot offer a moment. But yes, if any system of force tries to take the beam down, then beam will give a upward force. And if any system force tries to take a beam up, then beam will give a downward force. Understandable? So over here also, it can give a force in a x direction or a y direction, but not in a x direction. So this is a fixed hinge support. Fixed hinge support can give resistance in a two mutually perpendicular direction. Movable hinge support can give a force only in a reaction force only in a one direction. Got it? Now, if situation is slightly different, for example, if we have a beam which is fixed inside the wall, then or say it is welded over here with a plate, whatever. Then, if any system of force is trying to pull the beam in a rightward direction, it will pull the beam back in a leftward direction. If any system of forces can try to push the beam in a leftward direction, it can give a reaction in a rightward direction. Same way, this particular fitting will prevent a upward and a downward motion by giving a upward force and a downward force. Okay, if any system of force is trying to push the beam up, this particular joint will push it down. Also, if any system of forces is trying to rotate the beam, then also this particular joint will produce a moment also. Moment also, and that is a speciality of a fixed joint. Okay, now this is a fixed hinge joint. It can give reaction in a vertical direction, reaction in a horizontal direction, two things. If we have a fixed support like this, then this support can give a reaction in a y direction, reaction in a x direction, and it can provide a moment also in this direction. Suppose we have a roller support like this. Then it can give, you will agree with me, a force in upward direction only. Suppose we have a movable hinge joint. Then this hinge joint also will give a force in upward direction only. It will not give a force in a horizontal direction simply because there are two rollers over here which will not offer any resistance to the horizontal movement. So this is called fixed hinge joint. This is a roller joint. This is a roller supported hinge joint, and this is a fixed joint. They are characterized by the forces in this direction. They kind of a support reactions they give. Is anybody having some curiosity? Would like to debate some more debate? Confusion? Anything? Just ask me. Okay. Now, let us look at these supports. This is a beam on the top, and note the support over here, roller support. It is moving on the wheels. So these are simple upward reaction.
Excuse me, sir.
Yes.
So the white color isn't visible. So can you change the color and draw?
Yeah. Okay. Sure. Is this color visible?
Yes, sir. Thank you.
This is a crane, and here there are wheels. So roller supports, they give a upward reaction. We have a multiple supports over here. Sorry. It is this place. It is bolted fixed way. These are kind of fixed support at everywhere, which will give a upward force, horizontal force, and a moment in any direction you want to. Now here there is a very huge crane, and it has a movable support here, only capable of giving a upward force. Here also it will be so. It cannot resist a moment. It cannot resist a significant force in a horizontal direction either. Again, movable supports of a very giant gantry crane. This is a pinned support. It can resist a vertical movement and give a vertical force. It can resist a horizontal movement and can offer a horizontal force, but it cannot offer any moment. Roller support. It can resist a vertical movement by providing a vertical force. But it cannot offer a horizontal force because this is itself is movable. Fixed one resists a vertical displacement by giving a vertical force, resists a horizontal displacement by giving a horizontal force, and withstands a attempt to rotate it by offering a resistance to rotation. So this kind of a joint can give three reactions. One, two forces and one moment. Look at this gigantic beam. There is a pin support at the end. There is another pin support in this another bridge. There is an arc.
So are you showing some picture?
Yeah.
It is not visible on this.
Okay, I will, thanks for telling me. I will. Is visible now?
Yes, sir. Now it is. Earlier, if you were showing any pictures, that would also visible.
Okay. So now look at this. Here there is a pin joint which will, and it is fixed also. So it will resist a movement in this direction, movement in this direction, and any rotation this way or that way. Rotation will not be resisted because there is a pin about which everything can rotate. So this pin can give a force in a y direction and a force in a x direction. What kind of a joint is this?
Fixed
joint.
Fixed joint. It will resist movement upward. It can resist movement back and forth, and it can resist an attempt to rotate it. So at this point, you can expect a reaction force in this direction, reaction force in this direction, moment in this direction, etc., etc. Look at one gigantic railway bridge. It has a 3 roller supports which can move. Now you can see here this movement is possible, this rotation also is possible, but vertical movement shown in yellow is not possible because it can provide a force in a vertical direction. Simple block giving a reaction. Now simply supported beam, no roller, nothing. But as you can see, this rotation is possible. This x and y movement also is possible. Vertical movement is all resisted, so vertical reaction only over here. Here you can note a movable hinge joint, and here we have a fixed hinge joint. This is a canistered beam or a cantilever beam which is resisting a movement in a horizontal direction, movement in a vertical direction, and a rotation as well. So here there can be a reaction upward, reaction horizontal, or and a moment reaction. Now look at this. Can you hear?
No, sir.
Yeah. I need to
Hi guys, this is Structures Explained, and in this video we'll be learning about various types of beams used in mechanics. There are basically 6 types of beams used in mechanics. Beams used for finding out reaction on support are assumed to be massless and support if pinned on. And in this video we'll be learning about types of supports used in beams and reaction produced in them on loading. First of all, let us understand what a reaction is. Let us consider a block of concrete lying on the ground. In this arrangement, the block is applying a force of mass times acceleration to the ground. In return, the ground applies equal and opposite force as per Newton's third law of motion. This force is called reaction. Now let us see various types of supports and reactions they generate when applied by force. First we will see a simple support. In this support, the structural member simply rests on an external frictionless surface. This kind of support allows rotation and horizontal movements, but not vertical motion. Hence it produces only one reaction to the applied force, which is perpendicular and away from the surface. Next we will see roller support. This support has wheels on the bottom and a hinge to attach members in it. The surface can be horizontal, vertical, or sloped at any angle. While assuming this support in calculations, all surfaces and the hinge are assumed to be frictionless. This kind of support allows lateral movement and rotation but does not allow vertical motion. Hence it produces a vertical reaction to the applied force. Value of moment will be 0 at roller support as it allows rotation. A roller support is generally represented in mechanics in this way. This kind of support is found in large bridges, which allows thermal expansion and contraction of the bridge. Next comes pinned support. This support is fixed at bottom and has a hinge to attach members in it. The surface to which support is attached can be horizontal, vertical, or sloped at any angle. This kind of support allows only rotation and restricts horizontal and vertical movements. Hence it produces two reactions to the applied force, one in horizontal direction and other in vertical direction. Value of the bending moment will be 0 at pin support as it allows rotation. Pinned support is generally represented in mechanics in this way. This kind of support is also found in bridges and trusses. So will the pin support or roller support always allow rotation? The answer is not necessarily. If the roller or pin support act as intermediate support in continuous beam, then it will resist the rotation. In this illustration, the continuous beam is loaded uniformly. Dashed lines show the deflected shape of the beam where end support allow rotation but middle support resist the rotation, and zero moment at the ends and some value of moment in the middle. Next we will see rigid or fixed support. This kind of support restricts any kind of motion, hence we will see all three reactions, which are horizontal reaction, vertical reaction and a moment. This type of connection is used in concrete framed structure or in this case a cantilevered beam. They are represented as a single line for structural members and a hashed vertical line for fixed support. That's it for this video guys. If you enjoyed this video and found it useful, hit that like button. Comment below your thoughts or questions regarding this video. More such content will follow, so do subscribe the channel and hit the bell icon to get notified for new videos. Also check out our social media pages, links to which are in the description. Thanks for watching, see you in the next one.
Fine, friends. It is 4:57, and time for you to take some long break, get your tea and the snacks, and get ready for your last lecture. So I will take your leave. Jai Hind to everybody. See you soon tomorrow.
Jain sir.
You sir, Jain sir.
Yeah, sir.
Here, kindly keep a record of today's attendance. Make a note. If CR is not there, Deputy CR should do that.
Yes, sir.
Yes.